In this video, we are going to talk about inverse functions and relations. First off, inverse means it's something that undoes the original. We're all familiar with inverse operations when we solve equations. So x plus 2 equals 8. You would perform the inverse of addition, which would be subtraction. So what it does is it just brings you back to the original. An inverse is a reflection across the y equals x line. So if you think about that, if we've got a parabola, it passes the vertical line test. Remember, the vertical line test tells you whether something is a function or not. So this function passes the vertical line test. When we reflect this across the y equals x, we end up with this that is not a function. But if we consider this y equals x line here, you can see that vertical lines are, when they reflect across, are horizontal lines. So with this horizontal line through the parabola, we reflect it across the y equals x, that becomes that vertical line. So we can take an original function here, obviously passes the vertical line test, but it fails the horizontal line test. It crosses this graph two places. What that means is when we flip this over, the inverse is not going to be a function. So the horizontal line test tells you whether the inverse, notated by this f to the -1, this is read the inverse of f, is a function or not. And the last part here is, how do you find an inverse? You're going to switch the x and the y. Remember, if we've got y equals x line and we reflect it across that, what I'm doing is my point AB becomes my point BA. So what we're doing is we're switching the x and the y. So let's take a look at a function. F of x equals x plus 3 squared minus 5. So we know a lot of information about this. We know that it's a quadratic with a Q, not a G. This is a quadratic. I know what my domain is. For a quadratic, my domain is going to be all real numbers. So x is a member of all real numbers. I have my range. Remember, for a quadratic, a parabola, it has no reflection. My vertex is at -3, -5. So that means all of my y coordinates are going to be above this -5. So y, such that y is greater than or equal to -5. I can find my x-intercept by setting y is equal to 0. So if y is equal to 0, I get my 0 equals x plus 3 squared minus 5. So 5 is equal to x plus 3 squared. Take the square root of that. We get plus or minus the square root of 5 is equal to x plus 3. So my x-intercepts are going to be -3 plus or minus the square root of 5. So -3 plus or minus the square root of 5. My y-intercept, this is what I'm going to get if I set x equal to 0. So setting x equal to 0, we get 3 squared, or 9 minus 5, which gives me 4. So 0, 4. Oops, we missed the comment 0. There we go. Can we find other things? We probably can, but let's look and see about the inverse itself. So when we find the inverse, what we're going to do is we are going to switch the x and the y and solve for y. So y equals x plus 3 quantity squared minus 5. I switch x is now equal to quantity of y plus 3 squared minus 5. Now this makes us uncomfortable. We're used to seeing y equal something. So what we're going to do is we're going to solve for the y. We get the y by itself. Adding the 5 to both sides gives me x plus 5 equals y plus 3 squared. To get to the y, I'll take the square root of both sides. So now we've got plus or minus the square root of x plus 5 equals y plus 3. And subtracting 3 from both sides, this is giving me a y equals plus or minus the square root of x plus 5 minus 3. So if we were to analyze my inverse here, so my inverse is going to be equal to plus or minus the square root of x plus 5 minus 3. I can find all of those attributes with the inverse. So my domain, remember that we have to have something positive inside this square root, which tells me that x plus 5, which is inside the square root, has to be greater than or equal to 0, which makes my domain the set of all x such that x is greater than or equal to negative 5. My range. So if we think about this, we've got plus or minus to the right 5, down 3. So we're going to have sideways parabola basically. And as far out as we go, we're going to cover all of those. Oops, that's the wrong way, isn't it? It should be over here. Sorry about that. But all of the y's are going to be covered. So y is a member of all real numbers. Now note here that my domain was the range of my original function. And my range was the domain of the original function, which should make sense considering the fact that in order to find the inverse, we flipped the x and the y and solved for y. So x-intercept, if I set y is equal to 0 here, so I would set y is equal to 0 equals plus or minus the square root x plus 5 minus 3, and solve for the x. I can move the 3 over, plus or minus the square root of x plus 5. And squaring both sides. This gives me 9 is equal to x plus 5, or we get x is equal to 4. So my x-intercept is going to be 4, 0. I can do the same thing with my y-intercept. Setting x equal to 0, I get plus or minus the square root of 5 minus 3. So then we would have 0 minus 3 plus or minus the square root of 5. And again, my x-intercept became my y-intercept became my x-intercept, which should make sense again because what we're doing is flipping that x and y. Now, if you notice, the inverse here is not a function, which should make sense considering my original function has a vertex at -3, -5. It's going up. My horizontal line test fails. We cross 2 places. So when this does get reflected across the y equals x line, we're going to have something that's not a function. But we can make it into a function by limiting the domain. So thinking about this problem here, I've got a parabola at -1, -3. It's going up faster than a regular one because it's being stretched by 2 vertically, with this point being -1, -3. Now, when I reflect this across the y equals x line, I will have -3, -1, something like this. This is a bad example, but there it is. I can limit the domain, say to the right-hand side, so the section that's increasing. I can set my domain to be the set of all x such that x is greater than or equal to -1. And what that does is that limits the function that I am reflecting to this right-hand side. So now when I find my inverse, I take my y is equal to 2, x plus 1 quantity squared minus 3, flipping the x and the y. X equals 2, y plus 1 squared minus 3. So now I've got 2, y plus 1 squared equals x plus 3. Dividing by 2, I end up with the y plus 1 quantity squared equals x plus 3 over 2. Taking square root of both sides, we get y plus 1 equals plus or minus the square root of x plus 3 over 2, or y is equal to plus or minus the square root of x plus 3 over 2, and then minus 1. Now the plus or minus goes away. We're only evaluating the positive side. So this minus thing, we can kill. So my inverse would be the square root of x plus 3 over 2 minus 1. We should rationalize, but we are going to save that for another time. Let's look at one more example. The next example I have is y is equal to 2 times the square root of x plus 3. Just a quick reality check. What is it that we're looking at? Okay, so we know that a normal square root graph looks something like this. We're going to shift this 3 units to the left, 1, 2, and 3, and we're stretching it by 2, so it's going to go up a little bit higher. So there's my original function. So I can look at my domain. X plus 3 has to be greater than or equal to 0. So my domain is the set of all x such that x is greater than or equal to -3. My range, since I can't, this is just a square root function, it's not a plus or minus, and this is a function, I'm not going to have anything lower than that x-axis. So y is greater than or equal to 0. Switching the x and y in order to find the inverse. So x is equal to 2 times the square root of y plus 3. Again, let's divide by 2. So we get x over 2 is equal to the square root of y plus 3. Squaring both sides is going to give me x squared over 4 is equal to y plus 3. And this gives me y is equal to 1/4 x squared minus 3. Now, understand that looking at this inverse, if you were just looking at this by itself, the domain would be all real numbers. But in this case, we are looking for a domain that is the reflection of this. range. So my domain is actually going to be the set of all x such that x is greater than or equal to 0. And that's going to give me the positive branch here. So that'll give me this. My range, this vertex here is at 0, -3. So I get the set of all y such that y is greater than or equal to -3. Now, one of the characteristics of inverses is that the composition of an inverse and its function should take you back to the original input. Now, what that means is if I take f of x is equal to 2x minus 3, I'm going to switch my x and my y. So x is equal to 2y minus 3, and I'm going to get my y by itself. So we get 2y equals x plus 3, or y is equal to x plus 3 over 2. Now it's a linear function, so we can turn this into 1/2 x plus 3 over 2, just as it's easier for us to see. But the concept we're looking at right now is that the composition of f composed of the inverse of x should take us back to the input, which is x. What that means is I'm going to take my f function, so 2x minus 3, and plug in my inverse. My inverse is x plus 3 over 2. You can see what's going to happen here. When I multiply the 2 times the denominator of 2, the fraction goes away, leaving me with the numerator, x plus 3 minus 3, which gives me just the x. And this works either f of the inverse or the inverse of f. We can also do this with numbers. If we take, let's do it backwards, the inverse composed to the function of some input, let's say 1, this should be equal to 1. So let's find f of 1. So that would be replacing the x with 1. 2 minus 3 gives me -1. I'm going to take this now and plug it into my inverse. So plugging it into the inverse, which was x plus 3 over 2, when I plug the -1 in, -1 plus 3 would give me 2 over 2, or 1, which is what we wanted. So this is a way to verify that the function that you found is actually the inverse. You can use it to check whether two relations or functions are inverses. I think that's it for inverses.